Hello and welcome to another digital design class. In the previous class, we finished the combinational logic circuits, which were circuits that didn't have any feedback, therefore they didn't have any memory, and the output for a combinational logic circuit changes with the input at that same time. Some examples of combinational logic circuits were such as decoders, encoders, multiplexers, demultiplexers, adders, so on. Now, we have another type of logic circuits that we call sequential logic circuits. The difference between sequential logic circuits and combinational logic circuits is that sequential logic circuits have a feedback system, meaning we would have usually a positive feedback from the output fed to a memory system and back to the input. And therefore, usually they have memory, and the output of a sequential logic circuit is not only depending on the input at that time, but it only depends on the output from the previous timing as well. So the difference between combinational and sequential logic gates, combinational logic circuits do not have any feedback, therefore they don't have any memory. And it's a real-time system, meaning the output depends on the input at that time. But sequential logic circuits, they have a memory and a feedback. Therefore, they have a memory because of the feedback. Now we have two main types of sequential logic circuits. We have asynchronous and synchronous sequential circuits. So again, we have two types of digital logic circuits, combinational and sequential. And the sequential have two subcategories. They could be either asynchronous or synchronous. So in an asynchronous system, we don't have a clock. The outputs change depending on the changes of the input, and we could implement those changes at any time, and therefore the output would change. But for a synchronous combinational circuit, when the input changes, we need to have the clock signal to be able to enable usually the signal to the system to change. So you need to have the clock for the output to change. So on its own, when you change the input for a synchronous, as long as the next clock doesn't arrive, the output would not change. So you need to have both the clock coming in and the input changing. And I will give you some examples. Now, one example, physical example that I give to the students that makes them understand this better, think as the asynchronous system as of a bunch of dominoes that you put in series, okay? And imagine each of these dominoes is for example, each of the dominoes is a logic circuit. So the thing is, one example of that could be this, is when you push the first domino, what happens? It hits the second domino and the third domino and so on, okay? And they're gonna all fall. So the last domino would not change until the previous domino has changed, until the previous domino has changed, and so on, okay? But a clock system is exactly like the shade that you have, these shades that you have. And usually they have a string attached to them. This isn't a good example. And at the same time, I can turn all the shades open or close. So this is going to be my clock. So If I connect all these dominoes with a string together and pull at the same time, what happens? All of them fall at the same time. And that's going to be the clock. In other words, the clock is synchronizing the outputs together. Okay, we want them to fall all at the same time. Therefore, we add all the clocks together, for example. So asynchronous and synchronous, the only difference is in the clock. Now, within the asynchronous systems, we have different types of sequential logic circuits, such as SR latch and different type of D latch and so on. And we're going to start with the basics of the latches. By the way, latch is technically a device that stores a bit of information. So it's the simplest, you can say, basic form of a memory, and it's pretty fast as well. Now, I think it's better to go on slideshow because it has these nice graphics that you can understand. So as mentioned, sequential logic gates, they have feedback, and this part is important. And the only difference between asynchronous and synchronous is the clock. Now let's start with the most basic sequential logic circuit. And by the way, this is an asynchronous system because it doesn't have any clock, which is called a latch. We're going to start with the most basic type of latch, which is called the SR latch. The reason that we call it SR latch is because it's also called the set reset latch as well. So we also call it the set reset latch. Now, initially, let's build a truth table for this. And let's initially assume that Q, the output, is 0. By the way, we have two outputs. We have Q and Q prime. Q and Q prime are the complement of each other. So if Q is 0, Q prime must be 1. Now, let's start the truth table for this. If Q initially is 0, and I give 0 and 0 to SR, what would Q prime be? And the new Q be as well. So if Q is 0, then 0 and 0 in the NOR gate. What is the result of the NOR gate, the bottom NOR gate, when the inputs are 0, 0? It's going to be 1. And now this one is connected to 1. Now 1 and 0, what is the NOR for 1, 0? Sorry, NOR, not or the upper one. It's going to be what? 0. Yes. So Q would be equal to 0 if we do that. And Q prime is going to be equal to what? 1. Now, in the second scenario, we would assume that S is 0, R is 0, and Q0 is 1. So if S is 0 and R is 0, then we would have 0 and 0, the NOR would be 1, and 1 and 0 would be equal to 0. So here, Q would be 1, and Q prime would be 0. Now, for the next scenario, we would assume that R is 1, and S is 0. And where did we get this, by the way? Let me go back a moment to show it to you. You can see that in the two first rows, Q is equal to Q0. Okay, what does this mean? It means Q does not change if we put S and R as 0, 0 or Q0 as 1. So as long as S and R are equal to 0, the output of this system would not change. meaning the next output, which is Q. By the way, we have Q0, which is the initial value. Q is actually Qt plus 1. So Qt is equal to Q0. And Qt plus 1 here is equal to Q. Okay, so it's the next output.
What are you considering this? So in our first step, we said that Q0 was 0. Where is that? Because Q and Q0 are always opposite of each other, right?
Yes.
What do you consider Q0 to be? Which one?
So Q0 is initially when you turn on the device. Usually it's 0 because you have 0 volts. But sometimes if you have an active low system, it's going to be 1. But this is just randomly. And I will show you what happens after 1-2 cycle. It will, fall into one of these categories. And I'll show you how it's done. But imagine you're given an IC, and that's a great question. Initially, when you turn it on, Q and Q bar, you could measure them. Q would be 0, for example, and we would assume that. If Q is 1, you can see changing S and 0 and to 0 and 1, it's going to change it, and it's going to reach a steady state. And I would explain how it's done. Now, imagine this scenario. Does it answer your question, or do you want? Okay, if it doesn't, so this is Q0, S0, and R0. They are just arbitrary. We pick them, random. When you turn it on, Q0, you can measure it randomly, maybe 0 or maybe 1. But as long as S and R are kept at 0, it's going to keep whatever in Q is. Imagine this is a memory, and you have data in it from the past. It's a flash drive. Flash drive actually doesn't work like this, but imagine that scenario. When you connect it, if you give S and R as 0, 0, it's going to keep whatever. It's as long as these two are 0, 0, it's going to keep the memory at the same that was initially what. So it's going to keep the initial value of the.
Where, when you turn it on, where would you measure Q0 at?
It's going to be the output of the IC.
Whichever one you consider the output is what Q.
Yes. Oh, that's a great question. On the IC, you would see they label which one is Q and which one is Q prime. Okay. Some ICs only have Q or only have Q prime, but on the IC, you would see it has a label, which one is input, exact same thing that you did in the lab. It shows which one is Q or which one is Q prime. You would know which one is Q, and it's in the data sheet of that IC.
Which one is Q0?
Oh, Q0. Q0, and that's a great question. Q0 is the initial value of Q, meaning the moment you turn it on, it's going to be Q0. And then you're going to find the next Q after that, Q after 2 seconds. That's going to be Q. And Q after, so it's like this. Imagine we have a time series, okay? Q0 is when you turn on. Then Q1 is after you change at 1 second, and Q2 is after 2 seconds, okay? But the thing is, if you have Q1 at 1, then Q1 would be Q0 for Q2. You know what I mean? So Q0 is always the previous input, and Q1 is the current input, the current output. So Q0 is the previous output, Q1 is going to be the current input.
So Q0 is the output, whichever word you choose.
Yes. Initially, you would assume that, yes. And I'll show you how it changes. I think if we go further, it's going to clear up a lot of things. So imagine here, if we are 0, 1 for Q and Q prime, okay? Imagine in this scenario. And suddenly I decide to change R to 1 and keep S as 0. Okay, let's see what happens. So this is 0, 0 and 0 gives us 1. And now this is 1. 1 and 1 gives us what? 0. So now we can find that it's stable, okay? Now let's assume that Q0 is now 1. Now 1 and 0 gives us 0, and 0 and 1 gives us what? 0. And then 0 and 0 gives us what? 1. And then 1 and 1 gives us what? 0. So now what I've done, I've flipped them. Okay. Okay, now that R and S are 1 and 0 and Q prime are 0 and 1, what if I change, and you can see this is the answer. What if I change R and S again? So I put R as 0 and S as 1. So, and initially Q was 0. So 0 is connected here. 1 and 0 gives us what? And 0 and 0 gives us what? 1. And then 1 and 1 gives us what? And 0, 0 gives us. So you can see that it stables after a few back and forths. So what happens is, again, it's the outputs are changing. It's flipping. So you can see now Q is equal to 1. Oh, sorry, yeah. We did, yeah, for this one, it's going to be 0, 1. Yeah. Now, what happens if, again, Q is 1 and Q prime is 0? 1 and 1 gives us 0. 0 and 0 gives us 1. Now it's, again, the same thing. It doesn't change. Now, what happens if both of them are 1? 1 and 1. 0 is here. 1 and 0 gives us what? 0. And then 0 and 1 gives us what? And then 0 and 1 gives us what? 0. So now Q is equal to Q prime, which is equal to what? 0. But since this is not acceptable, Q cannot be equal to Q prime. They must be opposite. Then this part, it's going to be equal to 0, 0, which technically it's unacceptable. And it's the same thing when it happens when S and R are 1 and 1. Again, this is going to be 0, 1 and 0 is going to be 0, and 1 and 0 gives us 0. Now, these two at the bottom are going to be invalid, what we call invalid situation. Here, the output is 0. Here, the output is 1. And when Q is equal to Q0, when S and R are equal to each other and equal to 0. So the table for an SR latch is going to look like this. When S and R are 0, the current Q would be equal to the previous Q or the initial Q that we had. When S is 0 and R is 1, we have reset, and therefore Q is 0. And when S is 1 and R is 0, then we have set. Q is equal to 1. And when S and R are both 1s, Q would be equal to Q prime, which is equal to 0, which is invalid. Okay?
If you did give both inputs 1s.
Let's do what, yeah. Okay, that's a great question. So what's your question, please?
This state right here.
You want to give both of them 1. Yes, that's great. And what do you want your input to be?
The input's 1.
1 and 1. That's a great question. So if this is 1, the other input of this would be 1. The other input of this would be 1. So 1 and 1 gives us what? 0. Yes. And then 0 comes down here, and 0 and 0, 1 gives us what? 0. And then this becomes 0. And 0 and 1 is 0, and 0 and 1 is coming. Yes, just flip back. It's like a, you call it? Yeah, a domino or something that goes back and forth until it's, it stabilizes. So whatever you give it, it doesn't matter. As long as R and S are 1, 1, and we don't care about Q technically. Q would be equal to Q bar. It's going to be 0, 0, okay? And we can do it for another scenario as well. Imagine R and S are 1, 1, okay? Now let's change R and S. Let's change R to 0. Imagine initially R and S are 1, 1. Now I want to change R to 0. So this is 0, 0. 0 and 0 gives us what? 1. And then 1 and 1 gives us what? 0. So 0, 1. So this is when R is 0, S is 1, and Q, the initial value with 0, and we don't care. Let's find where it is. It's this one. Sorry. This one. And what would Q be initially? 1. So Q went to what? 1. So we call it, this is a set. Set means output is 1. Reset means the output is 0. Is it clear? Yes. Let's, to clarify it, let's give another input. Tell me which input or which output you want me to change. Do you want me to change Q, S, or R? Or we can change all three. Or two, actually.
Can you show the example where all three of them are 1 again?
All three are 1. That's a great question. So if all three are 1, okay, and imagine the previous scenario. Okay, so 1 and 1, this one is connected with the feedback to the input, yes? So 1 and 1 gives us what? 0. And this 0 is connected back here. Now 0 and 1 gives us what? So the output would change to 0. Now 0 and 1 gives us what? 0. And 0 and 1 gives us what? 0. Now it's stable, okay? So give it 1, 1, and 1. What was the output? 0 and 0. Okay. So 1, 1, 1 gives us 0, 0. Or 1, 1, 0, which was the previous one. We started with 0, yes? Gives us 0. Now from here, tell me, for example, I want R to be 1, S to be 0, something like that. What do you want me to change? Let's do R 0 and S, keep it at 1, yes? And initially Q is 0. So 0 and 1 is what? 0. And then 0 and 0 is equal to what? 1. And now 1 and 1 is equal to what? 0. And then 0 is connected to 0 is 1. Now it's stable, okay? So if R is equal to 0, S is equal to 1, and our initial Q was what? 0. Initially we started with Q. Now what would Q be? And this is Q. It's going to be 1, and Q prime is going to be equal to what? 0. Technically, we don't even care what Q is. Now it's set, and when it's set, Q would be equal to what? 1. Now imagine Q is set, okay, and this is 1, okay. Now I want to change both of them to 0. Let's see what happens. 1 is connected to this. 1 and 0, nor 1 nor with 0 is going to be equal to what? 0. And then 0 is connected back here. 0 and 0 nor is going to be equal to what? 1. And then 1 again, nor with 0 is 0. So it's stable. So what happened? Did Q change? No. So when S and R are 0, 0, we would have no change in the output. Now, question is this. I want to change Q to 0 and Q prime to 1. How can I do that? So I want to change Q to 0 and Q prime to 1. How can I do that?
Set would be 0 and the reset would be...
Perfect. I just changed the reset to 1. Now, if this is 1, this 1 is connected to this 0. So 1 and 0 is what? 0. Now 0 and 1 is what? 0. Thank you. Now 0 and 0 is what? 1. And now 1 and 1 is what? 0. So what happened? And again, 0 and 0 is 1. We stabled it and we changed this to 0 and this to 1. Is it clear? So when we want the output Q to be 1, we would set would be 1, reset would be 0. When the output we wanted Q to be 0, then reset would be 1 and set would be 0. If we don't want it to change, set and reset at 0. You imagine you have memory that you want to keep the memory on it. You just put 0 and 0. It's not going to change the memory. And then if you put 1 and 1, it's going to put it in invalid. And now we'll explain how we can prevent the invalid situation. Yes.
Q0 Q0 is the initial value of
Yes. Yes.
Q.
Yes, the initial value of the Q at moment 0 or the moment before that output. Yes. Now imagine our initial value looks like this right now. Q is 0, okay? And Q prime is 1, okay? How can I change Q to 1 and Q prime to 0?
R to 0.
Okay. Okay, let's do that. Okay. So if I change R to 0, this is not changed. So 0 and 1 gives us what? 0. 0 and 0 gives us what? 1. Thank you. Now this changes. Let me do it like this. This goes to 1. Now 1 and 1 gives us what? 0. And then 0, 0, 1. So it goes to 1 and 0. So we changed R to 0 and S kept it at 1. It's a set, so Q would be equal to 1. I know it may seem a little confusing because it has 2 feedbacks, but actually it's a genius way to be able to have a control. And the good thing about this, keep R and S at 0, 0, or even disconnect them, connect them to the ground, and come back a week later, and you would see that Q and Q prime are both. As long as the latch is powered, okay? As long as you have power in the latch, it's going to retain the information that it already had. Okay, is it clear? And if we want to flip it, you just... Now let's go to the next slide. As mentioned, if S and R are both 0, it's going to be no change. If S is 0 and R is 1, the output would be reset or 0. If S is 1 and R is 0, the output would be set or 1. And if both are 1s, Q would be equal to Q prime, which is 0, which is invalid. Now, we learned that we can build all the logic gates using NOR and NANDs, okay? Now we built it with a NOR gate. We can also build this with a NAND gate. It's going to be the exact same thing. The only difference is with the set and reset, that and the valid and invalid, those just switch. And I could prove it to you as well. Let's do a small proof. Imagine initially S is 0. R is 1, and our Q, initial Q was 0, okay? Now, what happens if I change S to 1? So if I change S to 1, let me do it with a different color. Now, this is 1, and this would be 1. 1 NAND with 1 gives us what? 1 AND with 1 is 1, so 1 NAND with 1 is what? 0. So this 0 remains 0. Now 0 NAND with 1 gives us what? 0 NAND with 1. 0. Yes? Yes? Or 1?
No.
1. Thank you. And 1 NAND with 0 gives us what?
1.
1. Thank you. And now 1 NAND with 1 gives us what? 0. Thank you. And then 0 NAND with 0 gives us what? 1.
0. 0 with 0.
0 NAND with 0. 1. AND would be 0, so NAND would be 1. And then 1 NAND with 1 gives us what? 1 AND with 1 is 1. 1 NAND with 1 is going to be equal to 0. So now the output would be what? If S is 0 and R is 1, where is it? Then output Q would be set, or it's going to be 1, and we got 1. Right? Do you want me to solve another one? I see a lot of confusion in your eyes. Yes. So I used to teach a class like 6, 7 years ago. And after each class, I used to ask them, do you understand? And they would look at me like I don't know, found the cure of cancer? And they would say, yes. And after 2 minutes, I would ask them, did you not understand me? And they would look at me again and say, yes. So it was confusing. Do you understand or you do not understand? Yeah. So if you're not, it's okay. It's confusing. It was for me. Still, sometimes it's for me when it's complicated. We can solve 10, 20 examples so you can, fully understand it. Imagine, let's give it a different scenario. Imagine if S was 1, R is 0, and Q is 0, and Q prime is 1, okay? Now what I want to do, I want to change the reset to 1, okay? I want to change reset to 1. So 1 and 1 is 0, 0 and 1, NAND with 1. 0 NAND with 1 gives us what? 0 AND with 1 is 0. 0 NAND with 1 gives us 1. Am I correct? So again, we have 1 over here. Let me see if I've done it correct. Yes. Now, 1 NAND with 1 is 0 again, and 0 NAND with 1 is going to give me 1. So if R is 1 and S is 1, yes, 0, 0 and NAND with 1. 0 AND with 1 was 0. 0 NAND with 1 is 1. Yes. Again, 1 and 1 is going to give me 0. Yeah. So, and then in that case, you can see that what happens when S and R are both 1, we have no change. And here we had no change. Q and Q prime remained the same. There was no change. Now, imagine Q is 0, Q prime is 1. Now I want to change, so, and S and R were both 1. Now I want to change both of these to 0. I want to change this to 0, and I want to change this to 0. Okay. Now, if I change this to 0, 0 and 0 gives us what? NAND would be 1. 1 NAND with 0 gives us what? 1. Again, 1 NAND with 1 gives us what? 0, thank you. And then 0 NAND with 1 gives us what? 1. And then 1 NAND with 1 gives us what? 0. Now let's, yeah. Oh, now I'm sorry, I confused one part. I've changed R to 0. So now 1 NAND with 0 gives us what? 1, thank you. And this one is connected here. 1 NAND with 1 gives us what? 0. And then 0 NAND with 0 gives us what? And then 1 NAND with 1 gives us what? 0. Now let's change S to 0. So 0 NAND with 0 and with 1 gives us 1. 1 and NAND with 0 gives us 1. And then 1 and NAND with 0 gives us 1. Now both Q and Q prime are 1, 1, which is invalid because they can't be the same. Okay. So you would change the inputs, and then it's going to change the output until you're going to get back to a stable point. Do you want me to solve another one, or? Yes?
Is there a name for each of these, or they're both just SR latches?
These are both SR latches. We can build them with a NOR gate or a NAND gate. Unless you want to go deep into the IC, you won't even know 99% of the time, which is it a NOR gate or a NAND gate. The reason that we use any of them is because of speed, the output requirements, but no, both of them work exactly the same. Now, both of them have a critical problem. What is the problem? Is that in a digital system, Q and Q prime shouldn't be equal. So the problem is this invalid part. How can I get rid of this invalid part? Or the invalid situation, condition? Perfect. What was it? Yes, how should I connect the NOT gates? That's a great yes. We use a NOT gate. Perfect, yes. So the invalid situation only occurs when S and R are what? The same. So what I can do, I can connect S and R with a NOT gate. Okay, now there's no way that S could be equal to R. So there's no way that we can have the no change situation or the invalid situation. And I'm going to call it an S, and this could be an S latch, for example. So one way that we can fix that S latch, and I'll explain more about it in the later, is to connect the S and R with the NOT gate together. Now, another type of SR latch is called the controlled latch, or an SR latch with the control input. The only difference between this and the normal SR latch is that the SR latch with the control has 2 extra AND gates, which the inputs are tied together, and that's going to be our control. And when the control is 0, we're going to lock and we would have no changes. And as long as the control is 1, then the output could change based on S and R. So it somehow works like a tri-state buffer that we mentioned last time. When C was 0, it acts like a high impedance, and you couldn't change the output. And this is the same. The control basically locks in whatever output you had from the previous stage, and you're not going to be able to change that output. But when C is changed to 1, because again, when C is 0, regardless of what R and S are, their output would always be 0. And we know that R and S, when they are 0, 0 for a NOR gate, the output would always stay same. It's going to be no changes. And we can do the same for a NAND gate, but here in a NAND gate, we have to add 2 NAND gates at the input and connect that, connect their input, one of their inputs, and give it to the control. So as you can see here, sometimes that was a great question. Depends on the requirement. If we want to build a controlled latch, building it from NAND gates is going to be easier. Because here you have 4 gates that are identical. Here I still have to build these AND gates with NAND gates. So I have to put a NAND gate in front of it. I have to put another NAND gate to not that NAND gate. So I would need a set of extra gates if I want to build everything from a NOR gate, for example, from on the left one. But the right one is going to be easier. So it depends on what we want to build and the circumstances. Now, one way to, again, prevent the invalid situation is to connect S and R together and connect it with a NOT gate. Therefore, S or set would be the opposite of R always, or the complement of R. So S is going to be equal to R prime, in other words, or the opposite of. All the time they're going to be opposite. And but there would be another, not a problem, but another benefit of the SR latch was the no change situation. Okay, we want to keep that, and to be able to keep that property of a SR latch, we can use the control gate, and we can use the control latch and keep that control latch, but just connect the S and R with the NOT gate to each other and tie them to each other. Now what we have called, what we have created is called a data latch. And a data latch has 2 inputs. It has a D, or data, which is connected to the set, and with a NOT gate to a reset. And the control, which is connected to the 2 NAND gates, which then they are connected to the latch itself. So this is going to be our SR latch on the right. Now for a D latch, it's much easier. As long as the control is 0, we have locked the output, and the output would not change no matter what the data is. And when the control is 1, if we give the data 1, the output would be 1. If we give the data 0, the output would be 0. In other words, sometimes they call it the set latch as well, or D latch, or data latch. And this is the simplest form of a 1-bit memory. Okay, you can make the memory out of this, keep the memory by putting C as 0, or changing the memory by changing C and D. Now, this control can also be connected to a clock, or what we call a timing diagram. Now, why do we want to put a clock here? The reason that we put a clock and add this to a timing system is because we want to synchronize all our memories together. Imagine this is a 1-bit memory, and now we want to have a 1-byte memory. So we have to put 8 of them together in a stack. But we want to be able to change this memory thousands of times per second. And to do that, we have to be able to precisely synchronize them. So what I would do, I would connect the data to the data of the input, and I will connect all the controls together to a central clock. And through that clocking, I'm able to change them simultaneously. For example, if you want to push a MP3 or a picture, I can change all the bits at the same time using that clock. So synchronizing them, I can use a timing diagram. Now, how does a timing diagram work? Imagine if the clock goes from 0 to 1, back to 0 to 1, and 0 to 1. And initially, when it's 0, the data changes from 0 to 1. Okay. If C is 0 and D is 0, what would the output be? Q. Q would be equal to the Q0, initial, Q. Okay, which here we would assume it's 0. And then suddenly D changes. D changes to 1. So D has changed to 1, but C is still 0. And as long as C is 0, Q would not change. So Q would remain the initial value that we had. Okay. But at this point, D is 1, and now C is 1. Now, when D is 1 and C is 1, what happens to Q? Q jumps to 1. Okay. Now, C has gone back to 0, but D is still 1. What happens to Q?
Back to 0.
Why? So what happens when C goes to 0?
Oh.
We have no change.
It
stays the same, so it's going to just continue the same. Okay. But now D, you can see that D went to 0. Here at this point, D went to 0. But did Q change? Why? Because C is still 0. So as long as C is 0, we don't care about D. As long as C is 0, changing D would not have any effect on Q. Okay. But when the next timing comes and it becomes 1, we will look at D and determine the output based on that D. Now here, C has changed to 1. What is D right now when C is 1 at this point? What is D? 0. So D is 0 and C is 1. What would Q be? 0. So Q is going to drop to 0. And it's going to do the same thing as long as we don't have any other timing come in. Now for the next timing, again, C is 1 and D is 1. What happens when C is 1 and D is 1? Q goes to 1. Now you can see that D is actually correlating with the clock, and we can synchronize hundreds or thousands of millions or billions of these memories together and create a unique memory. Is it clear? So when we add the control, we're adding timing, and now we have a synchronous system. So the output may only change when C is equal to 1, and we have a change in the D. As long as the C is 0, no matter what we put as the data input, the output will not change. Now let's do it for another example. Now here, C goes from 0 to 1 back to 0, and D is doing this. Can you tell me how Q would look like? I want you to think on this for a few seconds. Actually draw it, and I'll give you a minute or two to think on this, and then I would solve it. So the clock looks like this, and the D is changing from 0 to 1, back to 0, and then again 1. Okay. Can you tell me when Q would change? Initially imagine that Q is 0, okay? Will Q change at this point? Who says well, yes? Okay, who says it's no? Good. What about the rest of you? Don't have any opinion? No? Who says it's changing? Who says it's not? So at this point, what is D? Goes from 0 to 1. But what is C still? So when C is 0, what happens? Doesn't matter. So this chain doesn't change, keeps on going. What happens at this point?
Then it goes 1.
Then it goes 1. Yes, because C now is 1 and D is 1. Now we go forward. What happens at this point? D is now 0. Does it reset? Who says it resets? Yes, that's correct, because this is 1, and this goes from 1, 1 to 1, 0, so it resets. What happens again at this point?
Turns back on.
Jumps back down.
Perfect, yes. And what happens at this point? Yes, stays at 1. Perfect. So we have 4 points that the output may change, and those points are when C is 1. The 2 in the middle, C is already kept at 1, so they can change. So what happens? Exactly as you mentioned, it's going to change when C becomes 1 and D is already 1. So at this point, it's going to keep 1 until D becomes 0. Because C is 1, we are allowed. So its control gives us a permission to change the output. As long as C is 1, we have permission to change. When C is 0, control, we don't have any permission to change anything. We have to keep it the same. So think as C or clock as permission. When it's 1, you only have permission to change anything. When it's 0, you're not allowed to change anything. You have to keep the status quo, everything that is already there. Now, control latches are level triggered. We also have edge triggered, which are used in flip-flops. And edge triggered could be positive edge or negative edge. So in, again, a control latch, based on the level, when control is 1, we can change. For a flip-flop, it's a different story. We change it when it's going from 0 to 1 or 1 to 0. Only at this point we can change it. And I'll give you some examples of these as well. Okay, I think it's enough for today. We are going up to the flip-flops. Next class, we will start with the flip-flops and the difference between a latch and a flip-flop. The reason I'm ending today's earlier, because we're going to have hands-on lab today. We're going to do full adder and half adder. I've already posted the lab manual I found. I used to have another one, but that one had the 40 series ICs, and in the lab we have the 74 series. So we're going to go into the lab and we're going to do half adders, and if we have time, full adders today. Okay, thank you so much, and I would see you next week.